Yes. All right. Thanks, Paul. And so let's move on. And now, with these generic mechanisms in mind, let's start thinking about some reactions and a little bit of new chemistry. But we first need to actually think of maybe about some old chemistry first. So hopefully this is going to be a review, but it sets up what we're going to talk about with organometallic reactions. And one of the key things we're going to see this semester, and what's really important, hope you're as excited about it as I am, is that we're going to form carbon-carbon bonds. So it's fun replacing chloride with bromide and so on. However, in organic chemistry, and for those interested in biochemistry and other things as well, forming carbon-carbon bonds is one of the most important types of reactions that you can have. It's a way of taking two small molecules and making a bigger molecule. So we've already seen ways of forming carbon-carbon bonds. One of the simplest would be to take a cyanide ion. So this is Na+, this is Cn-, a classic SN2 reaction. Let's kick out that bromide, and we'll just write it like this so we can see the cyano group. And we formed a new carbon-carbon bond here. So that's great. However, limitations is it's one carbon, just fine. And then also working with cyanide. So not necessarily the friendliest reaction condition. So let's see about a more general way of doing this, forming a carbon-carbon bond. Well, we could take an alkyne. And I won't go through it in the interest of time, but we know that the carbon-carbon triple bond here makes that alkyne relatively acidic, pK of like around 25 compared to 50. So 10 to the 25th, 25 orders of magnitude more acidic than sp3 hybridized carbon CH bond. So we could take a strong base like this amide, and in the first step, this can take this proton off, form the alkynide anion. Just put it down here. Keep this as this generic. I'll put the carbon there so it's a little easier to see. C- here, right? Which now in an SN2 reaction can attack this, say with that bromide. Now we'll come back over here and let's see what we have. So we have a inverted here, we have carbon triple bond to R. So that's quite useful. We don't have the cyanide. We could add all sorts of different groups here, different R groups. If we want the triple bond there, that's great. If not, we could reduce that. We know reactions to turn that into an alkene, right? Either a cis-trans alkene or all the way down to an alkane, H2 with platinum, palladium, or nickel. So there are some variety that we can have here. However, there are also limitations. I mean, we could use it like in this reaction that we have here. Let's just draw the product. We could deprotonate that alkyne with our base, and then we're adding on 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons that we have as our product. And then again, we could do, if we didn't want that alkyne there, we know several reactions that we can use to get rid of it. However, maybe we wanted to have an alcohol or other functional groups around, or not make an alkyne. It still seems like a limitation. So we'd like to have another way of forming carbon-carbon bonds, but is a very general way. And this is where these organometallic reagents really come in to be useful. So I'm going to scroll to the next page. And we're going to see 3 types of organometallic compounds, those based on lithium, magnesium, and copper. However, the middle one, magnesium, is the one that we're going to focus on the most. But we're going to cover lithium first because it's a little bit easier. So let's think about what we're dealing with these organometallic reagents. And then there's one key point here that really helps simplify things. So as we were discussing at the very beginning today, if we have something like a carbon-chlorine bond, we could draw a dipole in this direction. Chlorine is more electronegative than the carbon. And so what this does is it means, in this case, the carbon is electrophilic. And that's your classic first semester organic chemistry reaction. We're going to have some sort of a nucleophile come in, attack here. This is primary, so this is great for an SN2 reaction. Kick out that chloride and carry out a substitution reaction. However, now what we're going to see is let's use a similar species and let's put a lithium there. Now, I'm pointing to a periodic table that no one can see, but lithium is actually less electronegative than carbon. So what this does is it reverses the dipole. It looks like this. And so lithium is less electronegative. So I posted these notes ahead of time, so hopefully it's not quite as boring sitting there waiting for me to write things out. That's why when there's a partial sentence like this, preparation of organolithium compounds, that's there ahead of time, just to minimize the boringness as we're writing out the sentences. But anyway, so back to this, the lithium is less electronegative, which means now, let me use a different color so it look like the same arrow. So that this carbon now, rather than being electrophilic, like on the left, this carbon is nucleophilic. So what we're going to be doing is we're making new carbon nucleophiles. And if I can spell that right, let's try electrophilic. So one could actually think about it like carbon with some R group, that's that chain there. And this is not true, but it's a way of thinking about it, as carbon the negative charge, lithium with the positive charge. I'm going to put that in parentheses because that's our imaginary species here. Oops. So that's what we can start thinking about it like this. And we're going to see the same thing with magnesium. And there's a bit of a detail here. Just ignore it. You can kind of ignore it for now. Magnesium will have something else coordinated to it. But what we can be thinking about now is a carbon with a negative charge. Magnesium having a, oh, I already went ahead and put the bromide there. Let's keep it as X. With an R. And these don't have to be hydrogens, but we'll put it there like that. So again, we have our species where the carbon is nucleophilic. Oh, sorry, switching colors here. So again, we'll have this dipole. So this carbon is nucleophilic. Yes, how about is? Okay. And one more. We'll put it on the side here. I mentioned we're going to have lithium, magnesium, and copper. Copper, we could have two carbon species. We're going to see this one looks a little bit different. Let's not worry about the details. It's actually with a lithium species, copper, lithium. And so again, we're going to have a dipole. And we'll see this one probably on tomorrow. Dipole. Again, making the carbon to be a nucleophile. Now, I think on the PowerPoint that I put together that I'll post when we're done here, we'll be able to see that if you look in the periodic table, you'll see, however, that the difference in electronegativity between carbon and lithium is much greater than the difference between carbon and magnesium. And that is greater than the carbon-copper difference. So what this means is that this carbon-lithium has the greatest difference in electronegativity. So it's going to have the greatest dipole. So if we wanted to write it, we could have made this arrow here and pointing to the lithium one, really big, like really big in one direction, magnesium a little bit smaller, and the copper a little bit smaller than that. Why do we care about that? And that's because there's going to be differences in their reactivity. Turns out because this carbon-lithium difference in electronegativity is the greatest, that makes this carbon the most reactive in the most simple case, and the copper-lithium species the least reactive. And then the magnesium one sits in the middle in terms of reactivity. What what we'll see is that affects that there's certain cases where we want to use this copper species. We'll name that one later on. A lot of times the lithium species might be too powerful to use, and the magnesium species, the so-called Grignard reagent that we'll get to in a minute, is kind of in the sweet spot of the reaction to use. Okay, so now as we're going through, and I know it's a long time, it's a lot of material, but